So we're going to continue here, and we're going to talk about two-tier modeling. So in Mplus version 7, we've implemented an algorithm that is going to improve the performance of the numerical integration. And this is basically a new algorithm that is used with the maximum likelihood estimator for models with categorical variables. The performance is improved basically by reducing the number of dimensions of the numerical integration. This new algorithm actually can be applied in very specific situations, and those specific situations are that you have multiple factors that load on different indicators and uncorrelated between each other. And if you have several such factors that load on different indicators and they are uncorrelated, this numerical integration that used to take several dimensions of integration is now going to take just one dimension. We've implemented that algorithm. You can see here I'm again comparing to this program IRT Pro. So they've, the authors of the program published several papers where they criticized us. They actually, the editors of the journals, they kept on sending me these papers for me to review, and I kept on rejecting them and explaining that they're not doing the simulations correctly. And the papers got published anyway, but our response was basically to redo the simulations correctly, and we have these simulations as the previous simulation I showed for EFA with categorical data. We did all these simulations. They're a pretty difficult thing to do because actually they're easy to do in Mplus, but they're not as easy to do in IRT Pro because there's all kinds of issues that have to be taken into account when you do simulations. Anyway, here's basically we've compared 6 methods for, so this is basically a bifactor model. It's with binary variables, and there are 35 indicators here with 1 general factor and 7 specific factors, and each specific factor loads on 5 of these binary indicators. And you can see the methods that we compared, the new Mplus two-tier algorithm that basically uses numerical integration, standard numerical integration. We also used Mplus with Monte Carlo integration with 500 points and 5,000 points again. And we used Mplus with the Bayesian estimation for the bifactor model and weighted least squares as well. And also the IRT program with the two-tier algorithm as well. And the Mplus two-tier, of course, has one advantage here compared to Mplus Monte Carlo integration. It's just something that it's totally solid. There's no need to worry about the number of integration points or anything like that. So this 8-dimensional integration in this particular example goes down to 2-dimensional integration. And so it's extremely reliable and straightforward to use. And so, for example, here you can see this where it says the log likelihood value. That's actually the actual value. There's no issue, there's no error here at all. It's basically very precise. In fact, in some other simulation tables that are not part of our presentation here, we've actually compared the use of this log likelihood value to conduct chi-square testing, and the Mplus two-tier came out as the best method, as you would expect. As I just said, it's the most solid method. Here, basically, this design here is basically fully symmetric. So you have the 2 loadings only are reported here, basically, because you have the loading to the general factor and a loading to specific factor. And you can see the parameter estimates and the coverage of the parameter estimates. And here is again another table that shows and they're fairly good. Both the coverage and the biases are pretty small. There's some, for example, here you can see that the bias was quite reduced by increasing the number of integration points. But basically, the biases are very small with a two-tier estimator. And here, basically, the quality of the standard errors. And again, the IRT Pro program actually failed in the standard errors. They actually have an overestimation, which is in the EFA example, they had underestimation. In this case, they actually have overestimation of the standard error by about 50%. These ratios are supposed to be 1 if the standard errors are correct, and they're pretty much 1 for all the Mplus estimators. And they're not 1 for this for that other program. But so actually, that's a little bit surprising, actually, because you know, in the EFA, you know, for me, it's very surprising, sort of, because EFA standard errors are actually pretty hard. So I can understand, you know, somebody trying to do it and not be able to do it, but this one should be this should have been straightforward for anyway. So let me just give you some examples of where you can actually examples that can benefit from the two-tier algorithm. So here's a longitudinal example, and you have these 3 indicator variables that measure this factor and over 3 time points, and you have correlations between these factors. And you add also these specific factors which correlate the same items across the 3 time points. And that's a meaningful thing to do, because if the indicators are basically the same, you know, you could actually have additional correlation because it's just that the same indicator, using the same indicator over different time points. So these 3 factors, you can see they are uncorrelated, and they also load on completely different indicators. No 2 of these factors would load on the same indicator, and therefore these 3 factors will collapse down to 1-dimensional integration. So from a 6-dimensional integration, this model would require 6-dimensional integration in Mplus6, but in Mplus7 it will actually require only 4 dimensions of integration. And here's another typical bifactor example. This is from the PISA data, where you have the testlets, and you know, these are items that measure matability, and you have specific factors that correlate particular items. And again, these items here, they are uncorrelated, and they load on different indicators. So in Mplus6, this would take a total of 6 dimensions of integration, because there's 6 latent variables. And in Mplus7, using the two-tier algorithm, it's going to require only 2 dimensions, because all these 5 factors will collapse down to 1-dimensional integration. Just to tell you a little bit more about the two-tier algorithm, so that two-tier algorithm actually is already available in version 6, but you have to be really skillful Mplus programmer to know how to set it up. And so I doubt that many people would be able to do it. But so bottom line is this, that we've actually implemented this so that it works automatically behind the scenes. And what you, if you want, for example, if you want to do, so the algorithm actually, what the algorithm does is takes a model like this one, and it sets up a 2-level model, multiple group model, where this is a between-level factor, and all these become within-level factors. And it's also a multiple group 2-level model, where this is in group 1, this becomes group 2, this is group 3, and so on. So 5 groups. So behind the scene, Mplus will set up a 2-level model estimation with multiple groups. However, you know, you don't need to know anything about this stuff, because this is all done behind the scenes, and you don't need to, you just write the model the usual way, basically. And on the surface, basically, you will not be able to tell if it's a 2-level setup behind the scenes. But basically, so when the model becomes really complicated, it's what the Mplus program will do is actually will go into the model and try to figure out if there are factors that can be collapsed behind the scenes. And so if it finds such factors, then it will do that and automatically set up the model for you. But again, you don't even need to say as part of the Mplus input that this algorithm should be used, because that's done, everything is done automatically. And so with that, I think Bengt is coming on. Here you go.
It's a relay race here. Can you hear me? Okay, let's see. This is connected to a magnet hanging around my neck. It's not some religious artifact. Okay. So today I'm playing the role of the applied person. So now we're getting back to applied matters. I'm not really applied person, so I'm faking it. So we're going to talk about advances in multiple group analysis. That was on our agenda. It's one of the major themes here, and it will provide you with some knowledge for doing some interesting analysis on your own before you go to dinner tonight. So we're going to talk about the old dilemma of doing multiple group analysis, and I think the dilemma is mostly, oh my goodness, we have a direct delivery from Starbucks here. The service is impeccable here. A latte, please. Okay, so the old dilemma is that invariance testing, measurement invariance across groups that you need to be able to compare groups, is often very difficult to do. And the reason is that the measurement invariance doesn't hold perfectly most often, and sometimes doesn't hold very well at all. And you don't know if you can compare the groups with respect to the latent variable, whatever it is. And we'll see examples of that. We'll see a couple of, I think, 3 different examples eventually. And we're going to present you with 2 new solutions to this old dilemma. And the solutions are very different in nature, so we want to characterize them carefully for you. We're going to go back to Statistics 101 and talk about ANOVA. If you remember the ANOVA of your youth, last year, was a distinction between fixed and random, and it goes something like this. You have a distinction between making an inference to only the groups in the sample in the fixed mode, only, say, the experimental conditions that you have, like treatment control. That's predetermined. Versus the random mode, where you think that you have a population of groups from which the current set is just a random sample. And that usually corresponds to the number of groups, where in the fixed case you have a small to medium number of groups, and in the random mode case you have a medium to large number of groups. So this is fixed effect ANOVA versus random effect ANOVA, except now we go way, way, way beyond ANOVA situations to very general types of latent variable models. So here are the 2 solutions. We're going to keep referring them to as solution number 1 and 2, just to keep you oriented, because there's a lot of news that we're throwing at you. We're going to try to be reasonably pedagogical about it. Although we haven't taught this much, so we're not fully pedagogical yet. But new solution number 1 is the one suitable for small to medium number of groups. And once again, we're going to come in with the new BSEM approach that we just talked about in the CFA setting, where group is a fixed mode. Fixed mode means that we can do multiple group analysis. And we're going to allow for approximate measurement invariance in the sense of approximate zeros and cross-loadings. And the new solution number 2, which Tihomir is going to spend more time on, particularly tomorrow morning when you're fresh and rested, it is suitable for medium to large number of groups, as we said, and it's, surprise, surprise, it's a Bayes approach. but there's a base approach where group is a random mode. And when we say random mode then for group, it becomes like a cluster. Group becomes like a cluster unit, so it's two-level analysis. So when you take the view of inference to a population of groups, group becomes a cluster, and you slip into a two-level situation. So Tihomir is going to talk about a new base approach, two-level base approach, where you're going to see a first use of the random factor loading. It's the new bar F by approach. So for solution number one, we have to introduce some convenience features, and they all come out of the painful experience I had in the last couple of months of typing in very, very long input streams, and found that we needed 1, 2, 3, 4, 5 simplifications. So our interface programmer did that very cleverly, and it starts here with the story of Cuv. And as it says, Bayesian priors are typically specified as independent, so that parameter is independently distributed from that parameter, but the parameters can also covary, and that's accomplished by this Cuv option. So in model priors, for instance, if you have a regression model with y regressed on two x variables with labels a and b, you can specify an informative prior, mean 10, variance 4, mean 6, variance 1. And if you say covariance between those parameters 0.5, then you specify a bivariate prior for a and b with covariance 0.5, which translates to a correlation of 0.25, where the correlation is as usually defined by covariance divided by the standard deviation, square root of 4, square root of 1. See? Okay. Now, the Cuv option, why is that useful when it comes to multiple group analysis? Well, it's because we are looking at differences across groups in measurement parameters. We want the differences across group in measurement parameters to be small, right? That's it. Small. When it's 0, it's perfect invariance. You're going to get close to perfect invariance. And we note in equation 4 by stat 101 that the variance of a difference is the sum of variances minus the 2 times the covariance. So if you take a non-informative prior is one that has really huge variance, and really huge is 1,000 today. So we say variance 1,000, then a covariance of 999 plus 0.995 gives the variance of 0.01. You recognize that 0.01. So with a normal distribution, this means that the difference between the measurement parameters has a 95% chance of being between approximately minus 0.2 and plus 0.2 again, right? Small range around 0, perfect invariance in this case. And so you can say that by simply specifying like this. That's the explicit way of using Cuv, but we're going to use it in a more elaborate context. We're going to use it in a diff situation. We have a new option that says that the difference between them has a mean of 0 and a small variance. And that's the same as saying these two lines. So as soon as you can say it in 2 lines, then you want to say it in 1 line. And then you're not satisfied with that because you're going to work with so many parameters and so many groups that you have to do the do-diff option. And you're not going to be able, unless you're a very quick thinker and reader, you're not going to be able to penetrate this slide. But take it home and think about it tonight, because I don't want to take time on details. I want to take time on big ideas. But this makes it possible to loop over all of the parameters and all of the groups, making all of the measurement parameters close to each other across groups. Trust me. Auto-labeling is a way to give labels in these different groups. Now, we're going to do multiple group analysis by base. Since we do by base, we don't have the usual grouping option that we use in multiple group analysis. When we're in the base framework, we have to do multiple group analysis through mixtures with known classes. Statistically, it's the same, and one day maybe we'll hide it behind the scenes that we do it in that way. But for now, it's type equals mixture analysis and known class. So if you have 3 groups, you specify 3 classes here, typical mixture analysis. And then you can imagine that you would have to specify labels for all of these measurement parameters in all of the classes. That's not too bad when there are only 3 groups or 3 classes. But when you have 10, as we will see later this afternoon, 67 groups, it takes a while to type. So our interface programmer came up with the idea, per my prodding, that you can give that label in the overall part of the model, not the class-specific part, but in the overall, you give a general labeling scheme where the number sign takes the role of the groups. And the only thing you have to specify is 1 through 4, which is the number of factor loadings in this case. And then you can pick up these automatically labeled parameters in all of the groups in the model priors, where you do a do-diff over all of the different groups, all of the different variables in the different groups in this case. Saves an enormous amount of typing, as I can verify. If you didn't understand what I just said, that's okay. Let's stay focused on the big picture. We just want to keep approximate measurement invariance. So here's a new user's guide example, 5.33. And we're working with 10 groups to illustrate the simplification, which turns into 10 classes, as you see there. 10 classes. And we have a new and known class simplification. You can give the group as a list of groups like this, which was necessary when working with 67 hospitals that were not subsequently, consecutively, I should say, labeled. And what you do, the auto-labeling here for the measurement parameters for the F1 factor and for the F2 factors. This specifies labels for each loading in each group. And we want it also for the measurement intercept parameters, which are in bracket. And they are, the Greek word for that is nu, N-U. And this gives labels for all groups for all 6 intercepts. And you notice that all of the loadings are free, has an asterisk after them here, which means that we need to set the metric somewhere. And if you think about a multiple group analysis of the standard ML kind, we typically fix the first loading to 1 in all groups, and then let the factor variances be estimated in each group. An alternative also in the ML world is to hold loadings none fixed to 1 but equal across classes, fix the factor variance in one group and have it free in the other groups, still allowing the factor variances to be different across the groups. It's a second approach that we take here to have access to all of the measurement parameters, all of the loadings. So therefore, in one group, in this case in one class, in this case in the last class, we have to fix the factor variances to 1 to set the metric somewhere. And that is also the class that by default in mixture modeling has means 0. So I didn't have to say that, but I do it anyway. And then you do the model priors, you do the do-diff dance, and it comes out like this for the loadings and for the measurement intercepts. Very shorthand. The original approach that was 50 lines of code, so a lot is saved. This auto-labeling only exists currently for base, only for mixtures, only for known class, the intersection of those 3 conditions. But we liked it so much that maybe we'll extend it in the future. It goes together with model all free, which frees up, relaxes the defaults that we have in mixture modeling of invariance of parameters across classes. The only type of parameter that varies across classes in mixture modeling are intercepts and means, whereas factor variance, covariances, and residual variances are held equal across classes. And loadings and intercepts are also held equal by default when you have by in mixture modeling. So we free all of that. All of that is relaxed by that single statement so that we can do this labeling and BSEM analysis freely. New solution number 2. Let's take a moment to look at that, if you don't mind. Take a look at those formulas and see what they tell you. That's good. And who wants to come up to the front here and describe it? Isn't that nerve-wracking when people do that? Okay, so we consider a single factor, and this relates to IRT and factor analysis as well. And this, I'm trying to give you a foundation for when Tihomir goes wild here a little bit later. He's going to expand on this theme and do some fine variations on this theme. But remember this slide. So let's consider a certain factor indicator R, one of P factor indicators for a single factor eta. So when we talk formulas, we talk Greek and eta, and when we talk input, we talk F factor. So we have then the regular factor analysis model in equation 5. Nu is the intercept, lambda is the loading, and epsilon is the residual in equation 5. But note that we have two random indices. R is ignorable, that's the variable. But I and J are important random variations. I varies across individual. J varies across cluster, because now the group is a random mode. So J refers to the group, but it's really the same as a cluster. And it can be then decomposed. The factor for person I in group J can be decomposed into a group component and an individual within group component. And you can look at that as the factor eta between plus eta within, where the between has a J subscript and within has an IJ subscript. So in multi-level modeling, the whole story is in the subscripts, right? So you have to read subscripts, the things you usually ignore. But here you have to read them. And then you have also random intercepts and loadings. So that it's like a multi-level model, you pick up components in the first equation and write them out in the next couple of equations. So this is level 2 variation, so to speak. The intercept nu for variable J has the mean of nu. This is a mean parameter. And the residual, delta nu J. This is the residual. Same for the loading. Has a mean lambda for the rth indicator. And the residual delta. And we set the metric, because the loadings are going to be all free, we set the metric somewhere, and we set the within, this is variance of the z, this is Greek z or zeta, to 1. That's like setting the within variance to 1. And then we let the between variance be free, so its estimate is relative to the unit variance of the within. So variance of eta between, for instance, could be like 0.2. So out of 1.2, only 0.2 is between variation. Has to do with interclass correlations. But note one important thing here, the last sentence on the slide. The same loading is multiplying both the between and within level parts of the factor. This lambda here, the random lambda, multiplies eta ij, so it multiplies eta j and zij, the between and the within parts, with the same value. That is what you see in IRT. I have never in IRT seen anything different. And I think they're off. They're off. That's not the way to do it. It may be a good approximation at times, but learning from factor analysis, going back to Lee Kronbeck at Stanford and Kjell Härnqvist in Gothenburg, factor analysis says that you're not at all guaranteed that the same loading is relevant for both within and between. In fact, you may not even have the same number of factors. You typically have many more factors on the within than on the between. Going back to ecological correlations and the fact that correlations on the between level is much higher typically on the aggregated level than correlations are on the within level. And therefore, you can't take this for granted that this model is the way to go. So we're going to talk about the two versions here. Equal loadings are within and between, be they fixed or random, and different loadings and maybe even different number of factors. So keep that slide in mind. It's good to go back to basics. Here it is repeated at the top. These equations are exactly the same as on the previous slide, but I wanted you to look at them when we talk about two alternatives. A first alternative, as it says, is to say that the variation of the factor on between is 0. So the factor with random loadings has only within level variation. Instead, you can have a different, separate between level factor with non-random loadings measured by the random intercepts of the y indicators. Sounds complicated, but it is exactly what we usually do in regular two-level factor analysis. And you'll see an example of the input for that. So you see then that on between you have loadings lambda b, whereas on within you have loadings lambda r. You can add within if you want to. So that may be one alternative model to the standard IRT model. Another one is that you have between loadings, but the between loadings are equal to the random within loadings, but equal to the means of the random within loadings. Can't be the random part, but the mean part. Now, let's put that into action here. Example 9.19 in the new user's guide. It doesn't exist in the user's guide you have. We have a three-part example illustrating this. First, we take the standard, what I call IRT approach to it. And you see then you have two-level random. We do it in base. And we have the specification of these random loadings. I should have slide 113 up here. So these two slides correspond. The random loading that you see here in equation 12 on the right screen is the same as the S here. Is for 4 different variables. So we have one S for each variable. Bar F measured by y1 through y4. And each of those 4 factor loadings are random, S1 through S4. And we're going to estimate their variance on between. They're free by default, so we don't even have to mention it here. But you can note that the means and the variance of S1 through S4 are estimated on between as the default. Mean and variance of S1 through S4 are estimated on between as the default. And then this F factor has a within part. You can regress it on background variables that are within variables. You see they are on the within list here. And on between, F also has variation. F on W and the residual variances are free, where W is a between variable. So where in the formulas on the right do we have this stuff that I'm pointing at? Where does that appear? We're talking about the first model here. Before we get into the alternatives, well, look up here in equation 10. Eta is separated into eta B and eta W. Eta W is what we talk about here on the within level. It's eta B. Its variation and its regression on W is what we talk about on the between level. So right here, eta B, down here somewhere, and here, eta W. So there you have it. So that's new in version 7. And here you have a combination of new and old. That's part 2. That's the first alternative. When I say first alternative on the right slide, I mean part 2 on the left slide. Why is it part 2? Well, we still have the random loading, but since we don't mention F on between, the variance of F is 0. The variance of the factor with random loadings is 0 on between. So that corresponds to this sentence. The first alternative to this model is that variance on between is 0. And instead, you have a separate, different between factor, separate between level factor with non-random loadings measured by the intercepts of the y indicators, FB by y1 through y4 on between. That's the standard two-level approach to factor analysis. And these are not the observed variables. It's the across-cluster variation of the y variables that is here. So they are latent, continuous, random intercept variables, which are the indicators. That's standard two-level analysis of all the versions before. And so here's a separate FB. And like we said, there could be, you could have more dimensions on within than on between. And certainly differences. Now, part 3 then, that's the second alternative in slide 113. Second alternative is that the lambda b loadings are equal to the means of random factor loadings. Here's how you do it. Random factor loadings, separate factor on between, but the loadings have labels lam1 to lam4, which is equal to the means of the random loadings. So you can go through these different models and see which one is preferable. And I think we'll talk a little bit about how you analyze what's preferable, but let's not do that now. So those are the 3 alternatives. And with that, I'm going to hand the baton over to Tihomir. So we're going to mix it up much more now as we go forward, just to make it more lively and keep you awake.
Okay. So I want to just go back, just say a couple of things just on this slide here. So, you know, the Mplus strategy for what you can put on which level. So y variables or just observed variables in general, you can put them on both levels, right? And on the between level, that means the average for the cluster, essentially. It's the conditional mean, basically, for that cluster. So you can, here that means the observed variable, but here it's basically the expected value of that given that you're in that cluster. And pretty much we don't use latent variables to have the same name on different levels. Like, for example, here you see f has its one name here, different name here. And there's only one exception. But you can see in this example here, you can use f on both levels. And so that's a new thing, basically, that comes with version 7, and it's very specific for random loadings. And we had to do this because otherwise there's no way to accomplish that equation there. So that's a new thing where the latent variable can now be used on both levels. There is one other case where we use the same latent variable on both levels. It's something to do with numerical integration, which I won't go into. So I'm just going to show you some simulation studies about why you would have to do random loadings in general. But before that, I want to say something else. So I want to say that I think as a methodological person, I think we have to face the reality that the frequentist methodology is a little bit exhausted. I don't think there's that much. The forefront of methodological development, I think, lies in the Bayesian estimation. So I'm saying that as another encouragement to actually, try Bayes, basically. And, later in the afternoon, you're going to be sitting in front of the computers, you're going to do some analysis. And if you've never done Bayes before in your life, and just do it. Basically, just say estimator equals base and rerun it and see that it does the same thing. It's not. It's to the point now where it's just another estimator, and so you have to embrace it. Again, if you want to stay on the cutting edge of methodological development, I think you got to move that. You have to make that step. So back to this slide here that I want to address. I want to show you some simulations that explore what happens if you have random loadings in your two-level analysis and you ignore the random loadings and you treat them as fixed loadings. What happens to the your analysis? What are the drawbacks of treating your loadings as fixed? And then we're also going to talk about small number of clusters, analysis with small number of clusters, and how much of these random loadings can we use there. So here's a simulation study that it basically compares a two-level analysis with, we generate data according to a two-level analysis with random intercepts and random loadings. And we use two different analyses. One of the analyses we use the Bayesian estimator accounting for the random intercept and the random loadings. And then we're going to use maximum likelihood estimation, just taking into account only the random intercept, but pretending that the loadings are fixed. So, here you have all the parameters that are involved in this estimation. That's basically the residual variance on level 1, the intercept, the loading, the mean loading parameter, and that's basically the between level residual. And basically there's no between level factor here in this simulation. So you can see the results of this. I think that this simulation has basically 5 indicators and 1 factor, and no factor on the between level. So you can see the results that what happens with the maximum likelihood estimation. It gets biased results for the within level residual, and this is pre-poor coverage. Of course, the Bayesian estimation, which analyzes according to the true model, has almost no bias and pretty much perfect coverage. And the maximum likelihood estimation gives biased estimates for the residual, biased estimates for the mean, which is a little bit somewhat surprising, poor coverage. For the loading, you actually get unbiased estimates, but the standard errors are underestimated. So the coverage is pretty poor, and no problems here. So you can do the same kind of simulations also, the same simulation also with categorical variables. You have, of course, with categorical variables, when because we're going to again generate data according to a two-level model with random intercepts and random loadings. They are these residuals here, right here. These are basically the residuals on the between level. So these are the random intercepts on the between level. So because of these random intercepts, you actually have to use the weighted least square estimation. Is that obvious to everybody, what I just said? Okay, so so basically, how many dimensions of integration do we have in here? Because there are 5 indicator variables and 1 factor, and so you have 5 random intercepts, right, for each indicator variable, and so they are basically you have to have 5-dimensional integration to be able to do this with maximum likelihood estimation, and that's why you have to use the weighted least square estimator in a 2-level analysis. How many of you guys have ever used the weighted least square estimator? Right? Well, okay, how about for 2-level models? Who has used it for 2-level models? Okay, well, I guess it's, so I actually expected not as many hands up, but you know, this is something that's unique to Mplus. You know, Bengt started this program like 20, 30 years ago, and weighted least squares thing was the thing that actually made Mplus. So it was the unique feature of Mplus for 20 years, and our competitors eventually, try to, compete, and Steven Detroit was working for Mplus, and then he moved to Lizero, so he learned how to do this stuff, and he did it for Lizero eventually, and some of the other programs also caught up, but actually we came up with the weighted least square for Tuleo, so, and nobody has that part, so. So anyway, so back to this simulation. So what happens when you have categorical data and you pretend that the loadings are fixed? So in that case, you can see actually the situation is actually worse because while the Bayes estimator has pretty much no bias and very good coverage, the weighted least square estimator has much bigger biases, and the coverage actually is pretty poor for all the parameters, including the loading. So, so that's a little bit to convince you that you have to explore random loadings. Basically, they are the parameter estimates can be severely biased if you don't, and if you really have random loadings. And another little topic that I want to address is. We're starting to talk about many random effects here. We have random intercepts and random loadings, and we have like, you can have like 20, 30 indicator variables. And then you essentially, if you have 20 indicator variables on a single factor, if you have random intercepts and random loadings, this is right away you have 40 between level random effects. That's almost, it's a little, almost a revolution here because if you look at the papers that are published on two-level analysis, there's maybe less than 10 papers that have more than 3 random effects, is my guess. And the reason is because we've been doing this with maximum likelihood, and maximum likelihood runs into all kinds of problems with random effects on the between level. So so we're now talking about 40 random effects, and so how long do you think guys it takes to estimate a model with 40 random effects? It takes less than a minute. So Bayes really doesn't really care that there are 40 random effects. It becomes a straightforward analysis, and to the point that should you consider having random loadings or fixed loadings in a two-level analysis? Well, it doesn't cost anything to explore random loadings. And if they're not there, you're going to get the variances of these random loadings will converge to 0. So, there's no penalty for actually trying random loadings, essentially. But the point is that we have this new methodology that now can open up so many more doors, and it can explore so many more random effects on the between level. But the question is again, can we do this with small number of clusters? And clusters and groups here, we're going to use it interchangeably, for the rest of our presentation here. And basically, that's a little bit of the new Mplus philosophy, that you can treat multiple groups as essentially as clusters. But the question is again, can you actually do this when you have small number of clusters? Or more accurately, the question should be, if you have small number of clusters, how many variables can you actually have in the analysis? Because if you have p variables and you have random intercepts and slopes, you have 2 times p random effects. And the answer is basically on this slide. So the first step in analyzing these models is to actually treat the random effects as independent. And if you do that, if the random effects are independent, then you basically have no limit. At least I haven't, with my simulations, I wasn't able to find it. So even with 10 clusters, the model can work with, I worked with this model that Bengt showed you on that slide, basically this same model right there. And it works, if you have 10 clusters, you have 50 variables, which is the same as having 100 random effects on the between level, you can actually still get easy and nice convergence. Now, there is one issue that comes up when you have that many clusters on the between, that few clusters on the between level, is that you need weakly informative priors to eliminate the biases that occur for the variances of the cluster level components. So what that says is basically that when you have 10 clusters, now I try to convince you, priors don't matter. You have 100 observations in single level analysis, regardless of what priors you put in, as long as you're reasonable, nothing will change, basically. You have these things disappear asymptotically very quickly. The priors disappear. The information that you provide is in the prior will disappear. But now, in between level analysis, the number of observations here, the number of independent units is the number of clusters. So the asymptotics in two-level analysis are actually driven by the number of clusters in your analysis. And therefore, when you have 10 clusters, the parameters on the within level don't matter, because those parameters, you still have, the total number of observations drives the asymptotic there. But the parameters on the between level, specifically the variances on the between level, those parameters will be estimated from the 10 clusters plus the prior, but the prior has a lot more influence on the estimates. So, so if you have 10 clusters, well, I mean, anything that's less than 20 clusters, you should be concerned about what prior is being used in the two-level analysis. And what our solution to that is actually to specify weakly informative priors. And weakly informative priors is something that basically it's something that was invented by Gelman for some kind of a different situation, basically. But what it says is that it's still an informative prior, but this prior is a reasonable prior. Now, why I'm saying a reasonable prior. So what is if you say an informative prior from minus infinity to plus infinity, that's very often not a reasonable prior, because if you have a variable that has a range between 0 and 100, obviously the mean has to be there as well. And so you already know that the mean is between 0 and 100, right? So if you actually use an uninformative prior that goes from minus infinity to plus infinity, that's not a reasonable prior, because what it says is that the likelihood for this parameter to be above 1 million is greater than it's below 1 million, so essentially. So if you think about what the area of that, if you actually think the probability, because it's a uniform prior, the uninformative prior is uniform, so between the probability between the odds for the parameter to be between 0 and 1 is the same as between 1 and 2, and it's half between 1 and 3, so the segment. So, and if you put an informative prior between minus infinity to plus infinity, you say that values as big as 1 million are just as likely as values between 0 and 100, right? Which is not a reasonable thing to do. And basically, the reason you're okay with such priors is because any prior would really do at that point. So as long as you have enough observations, and again, anything 20 clusters or more is actually sufficient to eliminate the influence on the prior. But back to this concept, what is a weakly informative prior is something that's a reasonable and has a limited range, basically. And this actually weakly informative prior came from doing actually probit regression, and the same concept actually occurs there. And in fact, Mplus defaults actually now have, for probit regression, we actually use weakly informative priors. The priors in Mplus are reported in Tech 8 output, and in Tech 1 output, and you can actually go and check what the priors are, and you'll see, if you do something with categorical data, you'll see that we actually don't use priors from minus infinity and plus infinity, because these kind of priors are dangerous to use in probit regression if you have small sample sizes. Even with sample size of 100 there, you can actually run into problems. So that thing was found by Gelman that, really what you ought to do is actually put in a prior that has a reasonable range between, if you know that it's a logistic parameter, it's already clear that an intercept should be between minus 10 and plus 10, because it's a intercept in a probit regression. So Those are the reasonable values to get. Anyway, so back to this story here is that you can still do a random loading model even with only 10 clusters and 50 variables. You can still do this analysis as long as you assume independence, but you have to add to analysis weakly informative prior, so you get unbiased estimates for the various components. Now, that assumption of independence has some consequences, and if you actually ignore the dependencies between the random effects, what happens is that you get some kind of a underestimation of standard error estimates, as well as you actually get a decrease in the accuracy in the cluster-specific estimates, meaning the factor scores, basically. So there are some consequences of actually assuming independence between the random effects. They're not very severe, but there are some consequences. We would like to actually have a methodology to take into account possible correlations between the random effects. The easiest way to make correlated random effects is basically to introduce a factor analysis model for the random effects on the between level. But however, even for this model, this is the simplest model to introduce correlation between variables with just one factor analysis model. Even with this model, actually, you need to have twice as many, you have to have as many clusters as you have random effects, basically. So the number of clusters should be, even for a one-factor analysis model on the between level, the number of clusters should be greater than the number of random effects. Which, in a particular example, if you have 10 clusters only, that means that you can only have 5 variables. And one more push to actually get this resolved, we actually use the same idea as the Bayesian, the BSEM methodology, except it's a little bit different in this case. If you remember what Bengt was doing is he take these unidentified parameters that approximately 0, and he puts a little tiny prior over them and let the data push the estimates out of these ranges. And so the BSEM methodology there was a little bit about 0 parameters that we don't want to, the substantive theory tells us that there should be 0, but are approximately 0. Now, you can actually do this with non-zero parameters, and this is an example of that. Here, the way to go to actually correlate random effects on the between level is basically to take a one-factor analysis model on the between level and use the BSEM methodology to actually put in tiny priors with mean of 1 and tiny prior. And that one-factor analysis model is going to have the variance of the factor be free, and all the loadings are approximately the same. So, but when you have this tiny variance, if you actually set the loadings to be fixed to 1, then that's one solution. But of course, that means that all the correlations between the random effects are the same. And so you don't want that, and that's what it says, is that this sigma here is going to allow you a little bit of wiggle room to adjust the correlations between the random effects not to be the same. And so that basically methodology, with that methodology, you can actually correlate the random effects. You can have small number of clusters, and you can actually have the correlations be different across the random effects. So bottom line of this slide is you can actually do this even with small number of clusters. And with that, I think it's Bengt's turn again.
They just turned me on here. It's actually not me speaking, it's a recording. Okay, folks, how are you feeling? That's pretty heavy stuff at times, isn't it? Do you even know what a coverage is? It should be 0.95 or 95%. So if you have values away from that, you're doing poorly. Thank you. A little louder, please. So now let's talk about data and data analysis. Hospital data example. And this is an interesting story. I got inspired by a storyteller yesterday for the tour of Utrecht. He was not only a guide, but a storyteller, professional storyteller. He told us a good tale, didn't he? Yeah. Anyway, the story here is that there's a special issue of organizational research method, ORM, which means snake in Swedish, but that's beside the point. And he is the guest editor of that special issue is Michael Seifer, who was a former adopted postdoc after the Katrina disaster in New Orleans. And he was with me in my UCLA group for a couple of months, and then he moved over to Singapore, and now he's in a School of Management, I think, in Melbourne. And he's giving Mplus courses there, but more importantly here, he's putting together a special issue of organizational research methods on Bayesian analysis, because he wants to introduce that in the business world, organizational research. And in that context, then, I asked him for data. If we were going to write a paper on these new methods, we wanted to do it on data relevant for the organizational research area. And he suggested a data set collected by Shortell and others in 1995 in health services research. It has to do with hospital quality of service. And we have a survey of 67 hospitals, over 7,000 employees, and approximately 100 employees per hospital, although that varies quite a lot. And this instrument measures 6 dimensions in some instrument that apparently is well recognized in this world of application in the ORM area. We're going to focus on one factor, one dimension, which has to do with the leadership. And we're going to have 10 continuous variables. Although I say items here, I actually mean continuous variables. We're going to stay continuous outcomes for the rest of today to keep it simple. And going back to my earlier slides, we can then take 2 different approaches to this, 2 different paradigms. Either view hospital as a fixed mode, where we would make the inference to only this set of 67 hospitals, or we can view hospital as a random mode, thinking that this is a random sample of hospitals, say in the US, of a certain kind or size, and draw inference to that bigger population. If we are in the fixed mode situation, then we have the choice between an old approach and a new approach. And we also have that choice, old and new, for the random mode situation. So let's systematically work our way through these 4 different alternatives, shall we? Oh, you still have energy. All right, so we're in section 1.1 here, going up to 2.2. Hospital as a fixed mode and conventional multiple group analysis. By the way, Tihomir talked about conventional 2-level factor analysis, and he equaled that, and you may not have missed it, he equaled that to random intercepts only, not random loadings. So our conventional 2-level factor analysis that we've done in Mplus for years can be seen as a random intercept situation, randomly varying intercepts across clusters. That's maybe not self-evident if you haven't thought about it long and hard, but it's actually he's actually right. So it was always random intercepts only, not random loadings, which is good because most of the random action, the biggest variances, are in the intercepts, not in the loadings, as we will see again and again. And for those of you who've done multiple group analysis, you will will experience the same thing, that most of the non-invariance sits in the intercepts, not in the factor loadings. Therefore, the IRT, Roche people are right. They focus on the difficulties. They are the ones that are more important than the loadings. Back to this story. Hospital is fixed mode, conventional multiple group analysis. Let's just remind ourselves of things that are more earthbound than where we've been. And we are here. We have the familiar grouping option. And here you can see why I wanted us to introduce a more general way of giving the grouping information. This you cannot do in version 6. There are a lot of hospitals to go through here, and they're not consecutive. And we're going to do ML estimation. Back to ML. Nice to be familiar. I'm using all my 8 processors here. We have a simple model. Lead, as in leadership, measured by the items, lead 21 to lead 30, 10 of them. Isn't it nice to be back to familiar stuff? And familiar is also the maximum likelihood analysis chi-square test of overall model fit and modification indices. Serboom's inventions, I should say. And we hold measurement parameters equal across groups, which is hospitals in this case, resulting, as usual, familiar as well, in poor fit with many moderate-sized modification indices. And we have the situation where it's not easy to modify the model because they're all equally large and none sticks out. So we're sort of wrong in so many ways. I can really say that conventional multiple group factor analysis fails. Although you can try to modify and try to convince editors, but it doesn't feel right, does it? There's something, when it doesn't feel right, when you have to fiddle around too much, you're fishing in the wrong pond. You're in the wrong park. You need to think differently and use a different methodology. Here is one of those. Section 1.1 here. New solution number 1, but we're still in group as fixed mode. We're going to do multiple group BSEM, the new BSEM feature of version 7. What we did before lunch was actually version 6 stuff, the cross-loadings, but there was a preliminary for this. So we do BSEM here, and we have then multiple groups as classes in a mixture analysis, 67 classes. You didn't think it was possible, did you? But they're all known classes. We know who's in the classes. They're just known groups. And we have model all free, changed in the mixture default, as we say here. New lambda psi theta, we talk tech 1. We talk literal style parameter array names, throwing around our Greek. And we use the auto-labeling feature that I talked about, letting the number sign, or the sharp sign for those of you who play the violin and piano, in the overall section here for the 10 factor loadings and the 10 intercepts, setting the metric of the factor in the last 67th group. I use a do-diff dance like that. And you don't need to understand the details now. You'll have plenty of time later on this fall to penetrate the details. But interestingly enough, 67 group BSEM requires 2,142 parameters because we have all of them free. All of the measurement parameters and structural parameters are free across all of the 67 groups. So poor Bayes has to work in a 2,142 dimensional parameter space, and that's not an easy space to work in for Bayes, but Bayes does it, and that's the advantage of one other advantage of Bayes over ML. It does take time. On my June 2012 computer, it takes 3 hours, 7 minutes, and 35 seconds. You know, it's like a long, nice dinner, and then you come back and have these gorgeous results. It's worth it, especially if the dinner is good. And out comes BSEM estimates for, we're looking at the last hospital. Why do I say last? Well, because we have then the variance fixed at 1, only in the last hospital group, and the mean is fixed at 0 by default. And you see that we have then loadings here for this class and intercepts across the 10 variables. But they're not going to be the same for hospital 67. Where are we? 120. Oops. So we're going to play with the right screen for a while here to liven you up as you get tired in the afternoon. So this is hospital 66 on the last screen, on the right screen, and 67 on the left screen. And note that the loadings are not the same. Look at lead 21, 983, 880, This is the wiggle room that we allow with the prior variance of 0.01, wiggle room. And same for the intercept, 3.7 versus 3.68. And now we're going to estimate the different factor variance from 1 and estimate the different factor mean from 0. So this hospital are doing a little worse on the leadership dimension, whatever that means, but we're not getting into the substance of the items. A new feature as well is when you do this do-diff stuff, there's a new output section which gives you the measurement summaries in the following sense. Let's consider the intercepts. And look at one of the 10 items. Item 3. This output displays item 3. You see the second subscript here is 3, 3, 3, 3 everywhere. The first subscripts go from 1 up to 67. 67 groups, all talking about the intercept for item 3. And what is displayed? You want to have a summary. Here's a summary. Is the difference between the intercept in a specific hospital compared to the average across all hospitals. That's what you want, right? The difference between a given hospital and the average of all the hospitals. You find then we provide you with an asterisk. So look here, for instance, hospital 51 for item 3, significantly different from the average by 0.316 higher than the average, and significant. So hospital 3 is in this sense not invariant across hospitals. It deviates from the average significantly. And this asterisk is judged by base. So base has a 95% interval, and when that interval does not cover 0, then we reject that the parameter is 0. Question or clarification?
Do you have any means for multiple testing?
No multiple testing implemented so far. But that is an issue, yes. So you're talking about Bonferroni type of things. So here you have the average of the intercept for that item, which means something to the substance researcher, and the standard deviation in a base posterior standard deviation sense. So here you have the hospitals that stick out with respect to that particular item. You yourself, at this point, have to, I should say, this summary saves you a lot of time. I had to sit and do this difference specified in model constraint for a long time, but now it's automatic. But you yourself, so far, have to do the summary over all of the items. So here you get a summary for each of the 10 items with respect to the loadings and with respect to the intercepts, which hospitals give significant differences, which hospitals are non-invariant. And you give it, in this case, you vary the priors to see the sensitivity to priors. And in fact, in this case, you may want to have a different prior for the intercepts than for the variances. That's still something you want to think about. Maybe a little bit bigger prior variance for the intercepts because they can vary much larger than the loadings. You know, we talked about variance 0.01, which was for cross loadings. Loadings don't vary that much as intercepts. They can vary quite larger, right? So you may want to have a different variance prior for the intercept. In any case, with this prior, you have the group, you have the outcome that hospital 48 is significant. If you have a bigger prior, you add hospital 67. So both of these are significantly different from 0. Have significant measurement non-invariance with respect to the loading for item 1. So you see, you can sort of look at it roughly. You see that you have a lot of numbers on line 2. That implies that item 2 is sensitive to non-invariance across hospitals. Item 2 is a bad item. Best item seems to be item 10. So that's sort of an overall measurement quality piece of information that you can get. Item 2 and item 8 are poor. And actually, Tihomir did a corresponding analysis of these data using the two-level random factor analysis approach, and also found that those two items, I believe, were the one that stood out. So for those of you who are familiar with IRT, you always look for anchor items, items that are invariant across groups. Well, this would be, item 10 will be the closest to that. None of them is scot-free, but item 5 may be pretty good as well. And you see also that most of the invariance is in the intercepts, not in the loadings. I should say that is partly a power issue. That is, there's more variance in the intercepts, and therefore, sorry, there's less variance in the intercepts than in the loadings. You know, intercepts are first-order parameters. Loadings have to do with relationships with second-order parameters. First-order parameters can be estimated with more precision than second-order parameters. Therefore, you have more power in this case to reject non-invariance for intercepts than for loadings. So it's not only a substantive story, it's a statistical story as well. And let me continue, and we'll get back to the idea of the second solution, group as random mode. And this is section 2.1. Remember the 4 lines? Fixed mode, old solution, new solution. Random mode, old solution, new solution. We are in random mode, old solution. Old meaning conventional two-level factor analysis, which we have explained is the same thing as allowing only random intercepts, not random loadings. And we try to be pedagogical here once again, bringing in equation 13 as something to hang up the story on. Recall Stat 101, random effects ANOVA, individual I and cluster J. The model is a factor model. This is between eta J, variation across clusters, and within cluster variation. It's like decomposing Y, the observed Y, in 2 latent parts, the between variation and the within variation. Two-level factor analysis elaborates on the 2 parts. You can pedagogically draw here a little brace around the first 3 terms, or circle them like I do. This is the between part. This is YB written out in a factor model fashion. And here you have lambda, you have YW with the within subscripts for lambda, eta, and epsilon. This is a 2-level factor analysis. Alternatively, in 2-level IRT, you break up eta only into between and within part, and lambda will be the same for the 2 parts. Whereas in equation 14, lambda B is different than lambda W. Okay? So you have IRT and factor analysis brought together, and we don't think you should make much of a distinction between IRT and factor analysis. And they're one and the same, except IRT tends to focus on categorical items. So let's do this conventional 2-level factor analysis. Type equals 2-level, estimator equals ML. So in the maximum likelihood framework, and we do the regular 2-level factor analysis, the within factor of leadership is measured by these 10 items. We fix the scale of the factor to 1 and within. We, in this case, we hold the loadings equal across the 2 levels. So we take the IRT approach, and we let the between level part of the factor variation be estimated. So we interpret it relative to the fixed 1 over here. So remember, you have to fix the scale somewhere, fix the metric somewhere. It becomes harder and harder to see that, but you should go back to this slide, and there always has to be a at 1 somewhere in the story. And we ask for mod indices for all parameters, meaning that even parameter arrays that have not, it includes parameter arrays that have not been opened up by Mplus, such as theta, to talk about tech language, that is the residual correlations among the indicators. We'll get modification indices for them as well. And in fact, in this case, for the hospital analysis, we cannot reject that the within and between loadings are the same. So the IRT folks are right for this example, but not always. And you do that by regular chi-square difference testing. 2 times the log likelihood difference or the difference between the chi-squares, with the degrees of freedom equal to the difference between the number of parameters in the two. And we find that 10% of the total variance in the leadership factor is due to between hospital variation. And we can talk about that variance being split into between and within, because we have the same loading, so we know that we're talking about the same factor on the within and between level, right? If they were different factors, we couldn't talk about them that way. They're 2 different things. But we have no information so far about measurement invariance across the hospitals. Tihomir, however, tomorrow morning is going to tell you how you can tease that out. He's going to talk about variance of these factors, factor loadings and factor intercepts, and get back to the base factors. Here is where Tihomir theoretically jumps in and gives his 2-level random factor loading analysis version of the hospital data. But in the interest of time, we're not going to do that now, which is a euphemism for saying we didn't have time to prepare this before we got here. Instead, he's going to give a more advanced application tomorrow morning when you're rested, when we talk about binary variables in the PISA data and consider 40 countries instead of 67 hospitals. Instead, we're going to stay on a very applied course, because I know you're exhausted right now and you're burning, your heads are burning because of all of this new information. I would be exhausted and not be able to assimilate anything more if I were in the audience. So let's be really applied for the last couple of minutes before we take questions and give answers and go off and do computing. So in preparing for, in trying to get the right kinds of examples for these new methods, I pestered my colleagues across the world and, for instance, emailed Peter Schmidt and Eldad Davidov in Zurich, and I thought multiple groups, the strength now, the new thing, if you missed it, the new thing is that you can do multiple group analysis with many groups. In which kind of application do we have that situation? Cross-cultural comparisons, cross-country comparisons, which seem to be particularly prevalent in Europe, but maybe also in the US, and they have 50 states, so they can do the same thing. And here is an example from Political Analysis, a European journal, I presume, which I didn't know about until just before this. I discovered this article, and I discovered an article by Vermont that we're going to talk about tomorrow, so I guess that's a journal we should monitor. He talks about measurement equivalence of nationalism and patriotism in ISSP, which you probably know what it stands for. I don't. But it is a European survey, and in this case it concerns 34 countries. And these data come from that survey, and they are available to the public. So you actually have access to them this afternoon, should you decide to want to play with it. Modest sample size of 45,000. 5 measurements of nationalism and patriotism, expected 2-factor structure, and those of you who are experienced structural equation modelers should start to worry. This is not a healthy situation. 2 factors and only 5 indicators. That means that at least one of the factors, but one of the factors exactly, has only 2 indicators. And in my book, a 2-indicator factor is not a well-measured factor. And a 5-item, 2-factor model is a very weak model, or a model that's prone to misspecification, because the 2-item part has to borrow information from the 3-item part. My thumbs are the factors and my fingers are the indicators. And actually, you can't even have the 2 parts uncorrelated, because then the model is not identified. So if you're misspecified here, it hurts here. If you're misspecified here, it hurts here. It's not a good model. But it's a good model from the point of view of learning different kinds of techniques. And very often it happens that you have to work with these kinds of data, I guess because it's hard to come up with alternative items. And there are many other situations where you do these country comparisons. For instance, in educational achievement, you have TIMSS, which I think stands for the Third International Mathematics Measurement Study. Close enough. Do we have any math educators here?
Mathematics and science.
Third International Mathematics. What's the second M for? What are the two M's for? Mathematics and? We don't know. Okay, so let's get into it. First step, let's try multiple group CFA with AML, the traditional approach. Two-factor CFA with measurement invariance across all 34 countries, as you might predict, with 45,000 people, we will get a p-value of 0. More seriously, however, is that the group-specific misfit is evenly spread over the countries, and the modification indices show a multitude of similarly large values. You don't have particular measurements of particular countries that stick out. So you don't know how to modify the models. So let's think through the alternatives then, as you might this afternoon. EFA for each group. Go back to the EFA. Do you really see a two-factor structure? That's so often where people go wrong when we answer Mplus support, that they say, our theory says that there should be two factors. Let me impose two factors. And then they say, it doesn't fit. Why doesn't it fit? Our theory said there should be two factors. There's a big gap between theory and the data analysis. What's lacking is pilot studies that verify that the items you have written based on theory is actually understood by the respondents in the way you expect. Typically, they wouldn't. It's a huge step to go from theory to CFA. And the exaggeration in the last decade of CFA at the expense of EFA is very unfortunate, I think. I think you should always start with EFA until you build up enough knowledge to dare to go to CFA. And in fact, BASE is a very good way to go from EFA to CFA in a continuum of increasingly strong priors. Prior goes from wide variance in the beginning, that's a non-informative prior for base EFA, to stronger and stronger priors, that is smaller and smaller variances, which at some point may turn 0, the prior variances, which is the same as CFA. But you have that continuum, the whole spectrum, which is a time spectrum as you learn about your measurement items across time, which you modify based on pilot studies. People don't do that. They go from here to here, and then they are lost in a lot of misfit and poorly written papers. Had to be said. Okay, so EFA is a good thing to do, and ESEM can be done. ESEM is EFA, but EFA in SEM world, so you can do multiple group EFA. Multiple group EFA. You have that described in some of our topics from Hopkins, the videos. You don't have to, when you want to do multiple group analysis, you start with EFA and then you want to do multiple group analysis. And so far, before Mplus, you had to jump from EFA to CFA just to do multiple group analysis. You don't have to. You can stay in EFA and still do multiple group analysis. That's what ESEM is about. And it's really important and useful. And then BSEM for all groups. So let's see how that goes. First, EFA for each group. Let's take Australia. 2,000 people there. And EFA has only 1 degree of freedom with 2 factors and 5 variables. And chi-square is good. Don't know how much power that is with 1 degree of freedom. And lo and behold, it looks like you have the first 2 items seem to be measuring the first factor well. And the last 3 items seem to measure the second factor well. We have small loadings here. Here's a small, although significant as you might expect with 45,000 people, it's still a small loading. Same thing here. That is a little bit larger, but it's still below the traditional limit of less than 0.3. So it's a fairly good solution. You don't have too high of a correlation, so the factors seem to be separately defined in a reasonable way. And we're still in ML here. Let's do it for Germany. We have still a good fit. And we have last 3 items measuring the second factor well. First 2 measure the first factor well. But you see that factor loading greater than 1, and correspondingly a negative residual variance. That's a so-called Haywood case. Haywood was some researcher, I guess, that got negative residual variances. An unfortunate man. But we still get a solution. When those negative residual variances are larger and large negative, they actually stop you from converging, which happens for US. Troublesome US here, no convergence for EFA. And you get this scary message. Number of iterations exceeded, problem incurred, exploratory factor analysis with 2 factors. What do you do? That's the EFA message. What do you do in that case? Well, now you have a solution, and it uses our new little invention of the do option. So you do the model F1 through F2. This is the ESEM way of specifying an EFA. And we label the residual variances in the second line. Label the residual variances. And in model constraint, we say that all those residual variances should be greater than 0. So we look for a restricted maximum likelihood solution. So bar sign, number sign here goes from 1 through 5. So the do loop goes from 1 to 5. So we'll turn you all into programmers here. And here's the USA study. And since it's ESEM, it comes out in a CFA fashion, not columns next to each other, but you have F1 by and F2 by. But you see then that you have the 2 big loadings up there and the 3 big loadings down here. And the residual variance is held at 0. That's the best it can do. It's not negative, but you get a solution. And it actually is a reasonable fit, nominally significant. You know, the 5% significant critical value is 3.8, something like. So this is significant, but it's a reasonable fit at that sample size. So we have forced a solution for the US in this way. So that's using ESEM with residual variance restrictions, illustrating that feature with a little do twist. What about multiple group ESEM? So now we did group country by country. What about multiple group ESEM? Well, actually, you get no convergence due to large negative residual variances for many countries. And then doing that trick of constraining the residual variance to be non-negative, it does give convergence. But the measurement invariance model, as you might have guessed from the beginning, has a way too high chi-square, and you don't get a well-fitting model. And ESEM gives you modification indices, so once again, you will see too many large modification indices, and there's no way to elegantly modify the model into something believable and publishable. BSEM comes to the rescue. All right, this is the last step, folks. Take a deep breath. So, what is BSEM now? Do you remember? It allows cross-loadings to be similar, but it allows cross-loadings. There are 2 issues. It allows cross-loadings similar to ESEM. ESEM is like EFA and therefore allows cross-loadings. But it also allows for approximate measurement invariance. That approximate, the wiggle room issue, now in terms of equality of measurement parameters across these 34 countries. Here, however, it's a little twist on the twist. This is the solution is thanks to Tihomir's nowadays vast experience with mixing convergence issues in Bayes, and he suggests a different parameterization. Instead of setting the metric by fixing the within factor variance to 1 and having all the loadings free, he sets a metric by fixing a factor. An alternative is to fix the factor loading at 1 in one group and let the other group's factor loadings be approximately 1. So setting the metric by a factor loading instead of by a factor variance is what I wanted to say. So that's a trick that's necessary for BSEM. If you try setting the metric by fixing the within factor variance at 1, you will not experience convergence while looking at Tech 8 scrolling by on your screen. Multiple group BSEM input then with this twist is you have, looking down here, nationalism measured by V21 and V22, those two items. We give them labels. Auto-labeling, you recognize that by the number sign and the underscore. Number sign refers to the 34 different groups. And PAT is patriotism, measured by 3 items. And similarly, auto-labeling that, and auto-labeling the intercepts as well. So here, if you circle this, you have the auto-labeling of the measurement parameters, the major loadings, and down here we do the XLAM. Whenever I say XLAM, it's cross loadings, X for cross loadings as well. So you need 2 kinds of approximate things, approximate zeros for cross loadings, approximate measurement invariance across groups. Those 2 things in tandem, plus this different parameterization is needed to crack this hard nut of 34 country comparisons with only 5 items for 2 factors. So what's done here is in the first group, we fix the factor loadings to 1, and we set the metric here. Since we set the metric of the loadings in that first class, we choose to set the metric by the factor means to 0 in that group as well, which implies that we have to free them in the last group, otherwise they would be 0 by default. Minor details. And then we do the do-diff dance here for the first 3 lines. You can circle the 3 lines here for approximate measurement invariance of the regular kind with small variance prior at 0.01. And here comes the particular parameterization trick that Tihomir suggested. That is that the lambdas don't have prior mean 0 as over here, but prior mean 1. And it goes from group or country 2 to 34. So we try to make the other countries' lambdas be close to 1 as we fix them in the first group. That's still talking about measurement invariance, right? But just in a different way. They were 1 in the first group. We want the other groups to be close to 1, to be close to equal, starting from country 2. So those 2 lines are due to this special parameterization trick. I'm going to stand on this side, otherwise I get a crick in my neck here at the end of the day. And then you do here at the last line is the cross-loadings trick. So you have the first 3 lines correspond to the regular measurement or approximate invariance that we talked about. The second 2 lines are the special trick corresponding to setting the metric in lambda instead of the psi. And the last line has to do with the cross-loadings. So this is a tricky example actually. A final slide. This converges, this gives estimates. What do you do with these estimates? What are you interested in? Well, you're interested in looking at the factor means. The factor means for the 2 factors. And here you're concentrating on the patriotic factor. That's how you want to compare the countries in the latent metric. I mean, you have the indicators of factors, so the factors is the focus. And what I want to show here on this slide is that you want to have a sensitivity analysis in the sense of playing with a prior variance. Here you have 2 choices of prior variances. On the x-axis, you have the results for prior variance 0.01, and on the y-axis variance 0.001. You can do 0.02 also if you want. What are the dots? There should be 34 dots. 1 dot for each country. 1 dot for each country. And it looks like the ordering of the countries is not very much dependent on the priors at all. The ordering of the countries, it's the same. It may be some little deviations from that, but it looks very good, like there's not a big dependence on the prior. They're all along this line, ordered in the same way with respect to the y and the x-axis. Up here sits a very patriotic Russia. I don't know why. And with that, folks, I think we are done for today. And we're at slide 146, and we aim for 150 slides for the 3 blocks of 1.5, so we got pretty close to our goal. even with the slow start this morning. So let's take questions and answers. And are you mic'd up as well? So who might have any ounce of energy left to ask a question?
Can I just say something?
Here, you can say it here.
No, it's okay. So yeah, again, these issues about mixing and stuff like that. You guys get the point about why this actually happens and why you actually even have to think about this. Just only have two indicators for a raw factor. So the model is hard. So when the model is that hard, then you kind of have to be on top of the whole thing and do the parameterization. I can't remember why we even had to consider that, but
We didn't converge otherwise.
yeah, it didn't convert, but I guess but anyway, the issue is that it's just a hard model because you only have two indicators for that factor. Otherwise, if you had three indicators, that would not be an issue at all.
I don't think so, yeah.
So,
Question in the back.
In the previous examples where the variance, you have either standardized the observed variables or standardized the latent variables. It's time you can do that. But now, what does 0.01 mean as a applied variance? Should it have a different meaning for each observed variable? Or is it all the same variance?
So the question is about the prior variance and the relationship to the scale of the variables in the model, which you have to think about.
Especially for variance.
Yeah, so in this case, the variables are on the same scale, which helps a lot, which is different from Holzing and Schweinfurt. The variables are on a very different scale because it sums up different number of items. But this is all on a 5-category Likert scale. So you won't see very large variations in the variances across the variables or across the countries to really worry about that. But again, I think more practical experience is welcome by looking at how important it is to choose the prior relative to the scale of the variables in the model. I think that can benefit from more study.
Isn't it also a different hypothesis that if you standardize the factors and then say that the factor loadings are approximately equal, it's a different hypothesis than if you set them to 1 and then say
Now, well, you remember, though, that you have, say that you talk about maximum likelihood, regular multiple group analysis, you have two equivalent parameterizations. You can do the fixing of the factor loading to 1 in each group, say the one factor, and let the factor variances be free in all groups. And exactly the same solution, exactly the same chi-square is obtained if instead you hold the factor loadings not fixed to 1 anywhere, but equal across the groups, and fix the factor variance in one group and free in the others. So those were the two parameterization we played with for this example. But they give the same fit to the data. So if you standardize the results at the end, you will get exactly the same parameter estimates. So I don't think the search for misfitting items would be different. You're right that the prior plays in a little bit different if the factor variance is 1 or estimated as somewhat different than 1. But it would only be an issue if the factor variances are extremely different across the different groups, I think. But again, we need more experience.
Yeah, I guess I want to go for that. One way to think about this, you have 2,000 parameters and so on, but they're not real parameters here. These are parameters that, so you have 67 groups, right? These 67 parameters represent one parameter, but the way I think about this, they're not really 67 parameters. They're not, if you count number of parameters in the regular modeling, it will be 67, but this is one parameter with addition of white noise. And that white noise is basically contributing to more accurate estimates locally. And the same thing with in this case, these are not same in different scales in the different groups. It's just slight adjustments to the parameters within the group to make the estimation more accurate.
But we hope that this technology catches on, because we think it's quite useful in general for comparisons on very many groups that comes up in cross-cultural research. This example is particularly hard, and we just wanted to show you how one can try to avoid those difficulties. Ultimately, even with the last BSIM approach, I didn't show you, the PPP values are not good. That is, the model fit is not good. What could possibly still be wrong, you wonder? Well, there is one more component. There could be residual correlations between the items. That can also be handled by BSIM, as we discussed in the BSIM paper, but we didn't want to take that step now. More questions? Yeah, one more in the middle. Last question. Slide what? 112? I think you need a microphone. For epsilon, yes. For epsilon, you're right, yeah. Good eye. 38?
Just start 38 and it will also work.
No, it works for PowerPoint, but not here. No. Yeah, PowerPoint does it, but not this. 38.
That's right. Yeah. Yeah, it's for each partner, each call. And why do you say it's not enough? Because signs are not identified. You can get equivalent model by making minus lambda.
That's a standard factor analysis result. You can turn all the factor signs differently. It says that you measure inability instead of ability. It gives the same chi-square. It's that kind of indeterminacy that hurts Bayes. Doesn't hurt AML, but hurts Bayes. Okay, folks, you have been very good. We'll see you tomorrow bright and early, but we're going to hang around a little bit on the computer lab, off and on at least.
Give me 1 minute. First of all, let's check the data outside. Well, Bengt and Tihomir, thank you very much. So give them a warm applause.
All right.